Okay, section 5.4 now is the end of chapter 5 for us. And this is strong induction, and then we're going to talk about the well-ordering principle. So we have two things to talk about, those two things. Number one, we're going to outline what strong induction is. And then we'll go through a couple proofs, one or two of them. And then we'll look at the well-ordering principle and an example of that. So strong induction is very similar to regular induction. A lot of times the body of the proof after your inductive hypothesis looks virtually the same, but it's in your base case that things change. So the way strong induction works is we let P of n be a property or statement defined for integers n. Then we let a and b be fixed integers such that a is less than or equal to b. And then we suppose that number one, P of a plus 1, all the way to P of b are all true. This is our base case, our new base case. The base case for strong induction. So you can see it's stronger because we have multiple base cases from A all the way to B. And sometimes A and B are close, sometimes A and B are very far apart. The second thing in the principle, not the principle, but in the strong induction setup is for any integer k greater than or equal to b, if P of I is true for a less than or equal to I less than or equal to k, then P of k plus 1 is true. This is the inductive step, or the inductive hypothesis step. Then we can say for all integers n that are greater than or equal to a, P of n is true. And this is by strong induction now. So strong induction has a little bit more setup. It's a little more complicated in your inductive step, but it works very similarly. So let's walk through a proof using strong induction. So let's prove any integer greater than 1 is divisible by a prime number. Okay, so this is still an induction proof. So we're still going to start the same way by defining our P of n. So let P of n be that n is divisible by a prime given that n not greater than 0, we need greater than 1. And I guess I should have done this at the start, but n is an integer. Okay, so an integer that's greater than 1 is divisible by a prime. So this is actually a pretty good example to start with because they don't tell us what our fixed integers are going to be, a and b, from up here. So what you really want to think about is a should be your first case, would be your normal base case. So 2 would be our first integer. 2 is, of course, divisible by itself. So let's move this up. We can work here. So our base case is, and let n equals 2. That's our first one. And 2 divides 2. So 2 is prime. So the idea here is, in this particular proof, we want to get to a base case that is not like this, because this is easy. Right? We have a prime, it divides itself. So you think, what's the first non-prime? The first non-prime is 4. So n equals 3, and 3 divides 3, n equals 4, and 2 divides 4. Okay, so now we have a setup, an a to b. We've gotten rid of all the primes, and we've gotten to the first composite number. That's a non-prime. So now our inductive hypothesis will be to let P of k be true. That is, k is divisible by a prime given that P of I is true for I and k that are integers, and 2 less than or equal to I less than or equal to k, where k is greater than or equal to 4. So a lot more setup in our inductive hypothesis. There's a lot of things, and I don't always write these inductive hypotheses for strong induction perfectly. I'm sure the book does it better than I do, and you could probably do it better than I do writing this, but this is what we need. We need our P of k to be true. We need that to mean that k is divisible given that P of I is true, which means that I is divisible by a prime. And specifically, we need integers, we need this inequality, and we need k to start at 4, because that's our b. So what does this mean? Well, this means that I is divisible by a prime. Would P of K be true? Yeah. So I is divisible by prime for I from 2 through K. So what we're really looking at is K plus 1, because that's what our strong induction principle was talking about. We need P of K plus 1 is true, just like we did for regular induction. So we have two cases. Case 1, K plus 1 is prime. So if K starts at 4, if K equals 4, then K plus 1 is 5, and we have this case. So that's prime, but then K plus 1 divides itself. And that case is done. So case 2, which is the case that we really care about, is K plus 1 is not prime. So then there exists A and B integers such that K plus 1 equals AB, and we know that 1 must be less than A, must be less than K plus 1. Now you could do this with B as well, but that's fine. So from here, we can make the jump to 2 is less than A is less than or equal to K. Because remember, these are all integers, A and K. So if we reduce by 1 on the outside, well, A could be 2 and A could be K. So we know that A is between 2 and K inclusively. Well, this is exactly the format that which P of I is true. So A is divisible by a prime. Some prime P. So we have K plus 1 equals, well, actually, let's write that. Then A equals PM, where M is an integer. So K plus 1 then equals PMB, and therefore K plus 1 is divisible by A prime. So now we can finish this out. It's a proof by cases, and it's a strong induction, so our conclusion is going to be a little wordy. So what we're saying there, therefore, in all cases, what's happening to my paper? In all cases, K plus 1 is divisible by a prime, and so by strong induction, for all n that are integers and n greater than 1, n is divisible by A prime. And that's the end of our proof. So you may be looking at this and going, this feels unnecessary. It feels like we did a lot of extra work that we didn't need. So let's go back here. Notice that we didn't use the 3 and 4 case when n equals 3 or n equals 4. We just used it to set up our property. Now, that's oftentimes going to be the case. We don't always need 3 or 4 different terms in our base cases. Sometimes we just need 1 or 2. And if you just need 1, then you're really just doing regular induction. And as far as I know, every problem that can be proved with strong induction can be proved with regular induction. You can think of strong induction as a way to enhance your knowledge a little bit and think a little bit more critically about how to set up a problem that has no setup. This one's very difficult to use regular induction with because we're not inducting on anything. So while this can be done with induction, it almost never gets done with regular induction. It either gets done with strong induction or directly, because this is just another way of saying the fundamental theorem of arithmetic that we can factor into primes, because that's all we're saying here. So keep that in mind as you're working through these problems. If you're not sure how to start, think how you would start with induction, and then see if you need an inequality. So in this case, we didn't have anything to induct on. Right? If we used regular induction and we said, so if we said P of K is true, that is K greater than 1 is divisible by a prime, by a prime, and then we look at K plus 1, well, we've already shown that if P divides K, then P does not divide K plus 1. So what we have here is Pm plus 1, a prime times another integer. How do we get that a prime divides this? Well, it goes back to those same cases. Either it's prime or it's not, and then we're just inducing the fundamental theorem of arithmetic. But that's not an induction proof then. That's just a direct proof, because the same thing could have been done at K, assuming this didn't help us. So this particular proof gets done with strong induction because it gives us something to work with. It gives us that P of I from, in our case, 2 to K. So let's look at another proof here, and then we'll go on to the well-ordering principle. So we are going to prove to compute a product of n terms there are n minus 1 total multiplications performed. So when you multiply n numbers, you're really doing n minus 1 total multiplications. Right. So induction proofs, I'll start the same way. Define your P of n, so let P of n be the statement. The product of n numbers takes n minus 1 total multiplications to complete. So this is another good example of we could use regular induction, but it's not as straightforward. Now this one's actually easier to do with regular induction than the last problem was. But let's go ahead and start with our base case. So P of 1 is the multiplication of one number of one number, and if you multiply one number, there's no multiplications. Ran out of space. So 1 minus 1 does equal 0. That's true, but this isn't actually useful to us because we need to multiply multiple numbers. So we need to, at minimum, go to P of 2, which is the multiplication of two numbers. And this we know has one multiplication. And 2 minus 1 equals 1. Okay, so these are our base cases, P of 1 and P of 2. So now we've set up our integers, our A and B. So we move on to the inductive step now. Let's put this back, I guess. Not here. So our inductive step is going to be for all integers k greater than or equal to 2 if P of I is true for all integers from I equals 1 to I equals k, then x1 times x2 times dot 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 all the way down to xk times xk plus 1. So this is the product of k plus 1 integers. This equals, since this is our product of k integers, this has a product of k integers which has k minus 1 multiplications then if this has k minus 1, there's one more sitting right here. So we have k minus 1 total dots, basically, multiplication symbols, and there's one more. So x1 times x2 times dot 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 xk times xk plus 1 is one more multiplications and this is after the initial k minus 1, so k minus 1 plus 1 equals k total multiplications. Which is what we wanted. So by strong induction, the multiplication of n terms takes n minus 1 total multiplications. Now, again, with the last one, you're probably looking at this going, this feels like we didn't need strong induction, but it actually does for this one particular reason. So let's go back to the original statement. The product of n terms are n minus 1 total multiplications performed. So you can see in our base case why we would need strong induction here, and it comes down to probably what you all thought: when you multiply terms you have to have at least 2. Well, as it turns out, you don't actually need 2. You can multiply one term with nothing. We've actually done that before. We will be doing that. No, we did it at the beginning of chapter 5 with factorials. Right? 0 factorial is defined as 1 because it's one integer, one number, being multiplied by nothing. Which isn't quite right. It's not being multiplied by anything. It's just there. It's counting the one integer. So if you were to prove this with regular induction, you'd actually only be able to start with 2 or more. So you'd have a caveat in here. Your domain up in your original statement would be n has to be greater than or equal to 2. And those are the slight differences. Strong induction allows you to prove larger things, but larger doesn't necessarily mean better. It just means different. So we can prove with strong induction that this is true for n equals 1 to infinity, whereas with regular induction you can really only prove with n equals 2 to infinity. And in actual practice of multiplication, that's fine, because we don't multiply one number almost ever, except for factorials and a couple other places. So let's look at the well-ordering principle now. Paul. So the well-ordering principle says let S be a set of integers containing one or more integers, all of which are greater than some fixed integer. Then S has a least element. Now That's what the well-ordering principle is. If you are well-ordered, then there has to be a smallest. It doesn't necessarily need to be a largest, because it could be infinite. It's one or more. So you have a set of integers. This clause here saying containing one or more integers is to show that it's not the empty set. So in chapter 6, we'll be talking about set and set theory. Empty set will come up a lot. So we have to make sure that we don't have the empty set. We need at least one. If there's at least one, then there is a least element, one that is smaller than the rest. And if you're well ordered, that will always be true. If you're not well ordered, well, then you don't have a smallest value. You don't have a least element. So let's look at an example of how this works out. And this is really to bridge us from chapter 5 into chapter 6. So this will be the end of this section, and with it goes chapter 5. So we are going to determine the least element if one exists. If not, state why the well-ordering principle is violated. So we're going to start with the set of positive real numbers. So basically every time in this example we're asking, does this have a least value? And the answer is no. There's no least value. So I want you to take a minute to think about this. Pause the video and actually think about it. And I'm going to tell you the answer right now. So we're looking at 0 to infinity, but we're looking at reals. So reals are all the fractions. The fractions get smaller and smaller and smaller. 1 over a million, 1 over a billion, 1 over a trillion. But there's never going to be a least real number, because even in the interval from 0 to 0.00001, there's still an infinite number of things. And we can keep making this smaller, and it doesn't change the fact that there's still an infinite number of real numbers. And that's the key here, is these are reals. These are not integers. This is why the well-ordering principle needs integers, because on a given interval of integers, there is a smallest value. But on a given interval of real numbers, there's no smallest value, ever. All right, so let's look at another one. Let's do non-negative integers. Such that n squared is less than n. So again, is there a least value in this? And the answer here, once again, is no. So you've seen the trick here. I fixed that here. It's definitely integers. So pause the video and think about why this would be the case. Why is there still no least value? And I'm going to tell you right now. These are integers. So the smallest integer, 1 squared. 1 squared is not less than 1. Well, that means that this set is empty. There's nothing in it. And our well-ordering principle requires there to be at least one item. There's no items. There's no elements. So our well-ordering principle is violated. Okay. Let's look at non-negative integers. Of the form 46 minus 7k for k in z. So we need this to be non-negative. So 46 needs to be greater than or equal to 7k, which means that k must be less than or equal to 46 over 7. So that means k has a maximum because we have 6 less than 46 over 7 is less than 7. That's what we're looking at. So k has a maximum of 6. Does k specifically have a minimum? Give you a second to think about that. The answer here is no. K has no minimum. Because all we have to do is satisfy this inequality. So knowing this, we can ask the question now, does the set of integers of this form, 46 minus 7k, have a smallest value? Well, the answer here is yes, because these are non-negative integers. So while k has no minimum, k goes to negative infinity. (46 minus 7k) goes to positive infinity. So while k has no minimum, our integers 46 minus 7k do have a minimum. So what would be the minimum? Well, it's non-negative integers, so the minimum would be 0. But we can't get to 0, because to get to 0, but k would have to equal, as we know, 46 over 7, and that's certainly not an integer. So the question comes up, what is the smallest number? Well, 46 over 7 is between 6 and 7. That's not the smallest. We know as we go smaller, we get bigger positively. So based on this inequality, when k equals 6, 46 minus 7k would equal 4. And that's the maximum, so just look at 5. If k equals 5, 46 minus 7k equals 9. If k equals 4, 46 minus 7k equals, what is that? 46 minus 28. Excuse me. I can't do simple math in my head for some reason right now. 2 seconds. My brain hurts for some reason. So we're getting bigger, but this is as large as k can get. So this becomes the least element. That's the well-ordering principle. Regardless of whether you're looking at sets that violate the well-ordering principle or don't, A, B, and C, they're not always easy. So understanding that there is a minimum is easier than finding the minimum. So we can understand here at this point that yes, there definitely is a minimum value to these integers since they're non-negative. It has a built-in minimum of 0, but finding that takes a little bit more work. So that's the end of chapter 5. We'll be looking at sets and elements and stuff like that in chapter 6. But we shall end here.